Yeah, it's working. Yeah.
Perfect. Let's start with our brother. Hello, everyone. Welcome to another Kent seminar. Today we have our last speaker of the semester. We still do have a working writing workshop the week after Thanksgiving, so stay tuned. So today, last speaker of the fall semester series, we have Professor Lehe. Professor Lehe is a new faculty here at UIUC in the Transportation Group, and he has a Transportation Economics Master's from Leeds and a PhD in Transportation, well, Civil Engineering and Environmental Engineering from UC Berkeley. Today he's going to be talking about a very important decision that we make on a daily basis. So let's give a warm round of applause to Professor Lehe.
Okay, so I'm kind of covered. I don't need a microphone, do I? No. I'm going to cover two papers that are both concerned. They're pretty different from each other, but they're both. Oh, he already introduced me. Yeah, this is just my educational background. This is my picture. My research interests transportation economics and downtown traffic, kind of the intersection of those two. So mainly concerned with theoretical models of people making choices about travel in downtowns. Okay, so basically starting off with, these are two papers, but they both were motivated by the same type of thinking, of me thinking about things. That is, so these are the thoughts that kind of motivated the research. So first of all, it's that we often face what I would call a trimodal choice. We can make a lot of different decisions about travel in cities. When I say downtowns, by the way, I mean in a very broad sense of like, in the city environment, like traveling around campus would be, I would consider downtown traffic, where we're running into intersections fairly frequently, where we're traversing blocks. That would be opposed to intercity travel or commutes from the suburbs into the city, right? So it's travel within cities in a place like Chicago, but not just downtown Chicago. By downtown, I mean in an urban environment. In any case, so we frequently face what is at least a trimodal choice. So not traveling is one option. Traveling alone, and that tends to be costly but fast. So that could mean driving yourself and paying for your parking yourself, and maybe you'd even include the cost of getting a car. And then some kind of a way of traveling with others, which tends to be cheaper but slower. And that could be like when you take Uber. We don't have Uber Pool here or Lyft Line. Or in New York City, they have one called Via, but in most major cities in the US and many cities around the world, you have an option of a carpool option. So you literally have the trimodal choice in your app. You could turn off the app. You could get Uber X, or that luxury service. You could get this Uber X is a standard solo trip, or you could get Uber Pool, where you're going to travel with other people. So another thing is that people are heterogeneous. Okay, so this kind of motivated me because in many transportation economic models, it's a bimodal choice. If it's theoretical, at least in empirical economics, they actually have pretty complete choice sets. But when economists tend to model things, they'll tend to focus on the choice between 1 and 2, or between 2 and 3. And I was thinking, you really have a choice among 3 options. Another one is heterogeneity. So heterogeneity is important, not just as a fact of a world. People have different qualities, like different values of time, different trip lengths, but also if you don't have heterogeneity, if everybody is the same, then you end up having to create these equilibrium conditions in which the costs of all the different modes that people use wind up being the same, or in equilibrium, which is obviously not true. In real life, you probably choose, whether or not you choose bus or car has more to do with who you are than it has to do with the fact that bus and car wind up being equally convenient or something. So we need to make people heterogeneous in ways that make it so that some people don't travel, some people travel alone, and other people travel with others. The final thing that is a big deal and the hardest thing to take into account, and which is often ignored in modeling, is what we call mixed traffic, which is the fact that the shared mode is affected by congestion. So there's actually a pretty substantial body of transportation economic choices of car and transit, but it will tend to focus a lot on things like buses and bus lanes, or subways, things that are not affected by congestion, because as you'll see at the end, when the two modes affect each other, it's very complicated. You end up in this sort of spiral, right? And then the fact of people being heterogeneous too makes the whole thing very complicated. So people tend to simplify by just sort of dropping out the fact that the congestion of the traveling alone mode, whether or not you choose it, depends on congestion, but it also causes congestion, and likewise with the other choices. Again, accounting for mixed traffic just means the traveling with other mode faces congestion too. Obviously not traveling does not experience congestion. So if you're not familiar with economic modeling, so basically this is like theoretical economics, it's not empirical, so what's the point of it? Just a little background, because a lot of people here work on experiments and hard things. The point of it is to get qualitative insights, so things that you start off with some assumptions that people can kind of nod along with, like, okay, it makes sense, like trimodal choice, I get it. There'll be a simplified story of reality, but we'll try to make it complex enough to get interesting insights, but not too complex that the derivations don't make any sense, and it's just random at the end. So that's what we try to do, is try to get a qualitative insight so that we start off with some assumptions, and then by some derivations we wind up with something that's kind of surprising, and then we nod along to it, and we say, oh, but now, because of that, that phenomenon kind of makes sense. Like the one that inspired me, that got me kind of into this, actually was not about transportation, it was about cities. It's Paul Krugman, who won the Nobel Prize for his work on economic geography. He wrote a very highly cited paper that he wrote about why industries clump together. And he starts off with these assumptions that you can kind of nod along to, and then he has a bunch of pretty complex, sort of complex systems analysis, but you can follow along to it. And at the end, you wind up with these insights about why industries group together, why you have manufacturing belts and such. And that kind of inspired me. So anyway, so we're going to talk about two papers. One is what I call the bus paper. So it's about the choice among not traveling, taking a car, and taking a bus. And the heterogeneity of people is the most important one that we're interested in, is they have different values of time. And then the second one, which we'll just go over more briefly because it's still in progress. The first one is waiting, is being reviewed at Part B. The second one is we're probably submitted to Part B, or Economics of Transportation, next month. I'm doing that with Ayush Pandey. So first we'll go over the bus paper. So the name of it is Winners and Losers from Road Pricing in the Presence of a Mixed Traffic Bus Alternative. Okay, so basically the fundamental question of this is, suppose that people have different values of time, VOT. People can choose between driving, taking the bus in mixed traffic, and not traveling at all. So who wins and who loses from a toll increase? And by a toll, I'm talking about a downtown toll. The type of thing that's coming to New York City in 2021, which will be a charge to drive in the downtown. It also exists in Singapore, Stockholm, Milan, Gothenburg. Some Norwegian cities have a form of it. But anyway, so this is probably going to be a big deal in the future because our technology for tolling keeps getting better and our cities keep getting broker and our infrastructure keeps falling apart. So this is one of the ways. So Lori Lightfoot, the mayor of Chicago, recently gave a speech where she said, I'm sorry to say that we have an $860 million budget deficit. So she mentioned congestion pricing as like a possible source of revenues for the city because the city already has quite high taxes. So I don't think they want to boost the property taxes. So it takes a long time to do a congestion pricing system, but maybe in the next 15 years, we might see it in downtown Chicago. Okay, so anyway, so the big question is who wins and who loses from a toll increase? And by that I mean specifically which people with different values of time. So the structure of this paper is we start off, it goes progressively, so we start off with a model where there's no bus, actually, just to kind of get the feel. And this is based on a paper that was written a long time ago, like 1978, that was never very highly cited, but it's actually a beautiful paper. I kind of adapt it and make it a little bit more general, but this is not highly original work by me. So we talk about agents. So you might call them travelers, except they might not travel. So they're just agents, they're decision makers. They choose between auto, driving, home, which is what we call not traveling. And it really is a general idea of not traveling. It could actually mean traveling, but just not going to the zone of under analysis, the congested zone that we're concerned with, where the toll is. And then finally, those are the only two choices in this model. So the auto mode has some parameters, just two. TA is the travel time. We measure everything in TUs, time units, just to make it generic so that when I do my simulation, people aren't complaining like, actually, the maximum density is this. And then money cost is just PA. So here's the thing, agents are heterogeneous, they have tuples. Alpha is their value of time, this is what economists often use for value of time. And then V, so alpha is measured in dollars per TU, and V is just measured in dollars. It's what we call gross benefit, or GB. It is the sort of the benefit that you receive from taking a trip before you subtract out all the costs of the trip, the money costs and the time that you lose, right? So it's sort of like if I gave you a trip that you just teleported to your destination instantly, how much would you pay for that trip is effectively your V. So alpha and V. V is for value, or growth, I don't know, I could have chosen better variables, man. Alpha is for value of time. So that means that we can say something, there's this full cost of auto. For an agent with a value of time alpha, there's PA, the money cost, plus alpha times TA. So it's just your value of time times the trip duration. And then the utility of home is indexed. So we can choose indexes of utility to be anything. So every traveler's, because the V's are kind of synthetic, every traveler's V is like relative to just not traveling. So it's 0. So you can get 0 if you travel. I mean, if you stay home, and if you drive, you can get V, your gross benefit, minus your full cost of auto. So this is your utility. This is the utility you're going to obtain if you do drive. So we make a couple of assumptions. This is an easy one. Everyone has positive VOT. That's probably pretty true. People don't go on scenic drives in downtown Chicago very often. They don't try to make their trips longer. And then the other one, which is just synthetic and is just made for modeling purposes, is that every trip is equivalent. So every trip has the same travel time and for a given mode, be it auto or bus, and also it contributes to congestion equally. This is not realistic, but by relaxing it, we make it more complicated, but we don't especially get that much more insights. So we just make the assumption so that the model's comprehensible. Okay, so basically, what's the equilibrium for this model? Okay, well, you choose auto so this is the utility of auto, this is the utility of home. So you're basically going to choose to drive if this is positive. In other words, it means that V is greater than CA of alpha. So everybody with an alpha such that V is greater than CA of alpha is going to choose auto. Otherwise, you're going to choose home. So we can divide up the population. So this is a type of graph that we can use. So we plot an alpha V space. We plot the function CA. So everybody with a V above this line, every single traveler is represented by an alpha V coordinate. We said they were defined by this tuple, alpha V, their value of time and their gross benefit. So if your gross benefit is higher than CA of alpha for your given alpha, you'll take auto. If it's not, you'll take home. So that means that sort of the population, imagine, and we'll look at this in a second, a density plot of the population. Like I said, everybody is represented by this double alpha V. So you can imagine there's a bivariate density function giving the density of the population over those two variables. So if I were to plot that, it'd be like a bunch of rings, or you could do it in 3D. It'd be this maybe a big hump or a saddle point with saddle points or something. But in any case, everybody above this line will travel. There's only mass for positive alpha. There's mass for negative V. You could have a negative, like you just don't feel like traveling, but you're totally irrelevant to the model in that case, because you'll never travel no matter what, unless we pay you. So we just do this in the first quadrant. Does this make sense to everybody? So CA is, again, this function, so we know it has an intercept of PA, and it has a slope of TA. Okay, so there's a population division between home and auto. All right, so now we're going to look at, for this home auto model, the effect of the total increase. So we make some assumptions. So basically, there's two ways we could go about things. We could actually propose like a specific distribution of demands, and we could propose a specific traffic technology. But for now, we just sort of make assumptions that a lot of different models could obey. So we make assumptions about how the model behaves, and then at the end, we're going to do a numerical simulation, which we plug in actual demands, we plug in an actual traffic flow technology. So the first assumption is called elasticity. It's just that if I increase the toll, the travel time goes down, right? So this can be obtained in a lot of economic models, but essentially it just means that if there's a higher toll, there will be less traffic, and so the travel time will fall in there'll be a new equilibrium. So we index equilibriums by the superscript. So subscripts index modes like A, H, B for bus. Superscripts index equilibrium, so 0 is before the toll increase, 1 is after the toll increase. So PA rises from PA naught to PA1, TA falls from TA naught to TA1. So we basically include the toll and the money cost PA. We could have a separate term, but there's no real point. So what happens in our plot is that CA pivots. So we said that its intercept is PA, so its intercept rises, but its slope, which is the travel time, falls, right? So that means that it does this pivot. And because of this pivot, there must be this intersection, and we can divide the population down to 5 groups. The first group are the people that do not drive, that drive neither before nor after. Call them HH naught. So we name the different population groups by this convention that I made up. So the first letter is their initial mode before the toll increase. The second letter is what mode they choose after the toll increase. And then the sign, the superscript sign, be it a circle or a plus sign or negative, is their welfare change. You can figure out whether or not how their welfare changes by whether or not CA rises with the toll increase for them, right? So what you end up with is that because this has a higher intercept but a lower slope, it must intersect the CA which prevailed before the toll increase, right? So that means that everybody with a low, this is the point of intersection, it's kind of irrelevant, but alpha tilde is where they intersect. So everybody with an alpha with a value of time that's less than alpha tilde will be worse off because of the toll increase, right? So these people are the people that drive before and after the toll, and the thing is that they have a low value of time, so they don't really appreciate those travel time savings. Everybody dislikes the money cost, but some people like the travel time savings more than they dislike the added money cost. So these people who have a low value of time are worse off because of the toll increase. These people in AH have actually stopped traveling. So that's the whole reason congestion went down, is actually that they were worse off, and also they just don't even want to drive anymore, so they quit driving. On the other side, these groups have their mirror images for high value of time travelers. So these are the people that drive before and after, and they appreciate the time savings more than they dislike the added money cost. So they're actually better off because their value of time is very high. Does that make sense? So it's like, maybe they have to pay an extra $3, but their value of time is like $10 it's like $10 an hour, and they saved 30 minutes or something. So that would be $5 of travel time savings. And then these people are the people, they're better off too. No one ever thinks about this HA plus group. You only think about people being tolled off the road. But in fact, there's people that are tolled onto the road. These are the people that have a high value of time, but they did not travel initially because their value of time was so high. It was not worth it for them to drive. But then once it's faster to drive, they think, okay, I'll go ahead and drive. So every group below alpha tilde has a mirror image above alpha tilde. So people are both discouraged from driving and invited to, you might say invited to drive. And then again, HH has a circle because these people, it's totally irrelevant what happens on the road, they never travel. So you can see these are the slopes of the two lines. Yeah. So this overall, the whole point of this section is really to get the analysis set up for the next section where we're adding bus, getting you familiar with the conventions and terms and how to think about things. So again, imagine that there's a population distribution here with like a bunch of rings, like a contour plot. All right, so just to pause. So a lot of people, so this means the theorem is that the full cost of auto rises, falls for everybody with alpha less than alpha tilde, or it rises for everybody with, falls for everybody with alpha greater than alpha tilde. Okay, so a lot of people think this also means income regressivity, because the value of time is also correlated with your income. But actually, we cannot conclude anything about income regressivity from value of time effects, even if they're very strongly correlated. And I made up this synthetic example. It might be that the poor are worse off with tolling or whatever, but you cannot tell from this. And I made up this synthetic example in which value of time is highly correlated with income as just a way, so basically, in this very synthetic example, there's two income groups, a low income and a high income group. The low income group and each group has all of its population in 2 point masses, right? So these are the 2 point masses of the low income group, these are the 2 of the high income group. The average alpha of the high income group is higher than the average alpha of the low income group because they're correlated. Alpha, value of time, is correlated with income here, which is what we're looking for. But the way that I've arranged the dots is that when you actually increase the toll, the low income group ends up being better off by 8 cents. The dollars don't really mean anything. And this is supposed to say high income. And the high income group is worse off by 8 cents in total. So the reason that happens is that in this example, the gross benefit is also correlated with income, right? So that makes it so that the low income group had this point mass here that initially had almost no surplus. They were barely on the edge of even driving in the first place. They didn't really care that much about driving. Then when I increased the toll, they quit driving. So in a sort of an equity analysis way, if you looked at it, you might be very offended, like, oh, you told the only people that quit driving were low income. But if you really do the math and do the welfare analysis, the low income people are better off and the high income people are worse off. I'm not saying that that's the way the real world is. I'm saying that it was really easy for me to make a counterexample. So we actually can't conclude anything from the fact of low value of time people being worse off. It's just a statement that you would have to do a separate analysis of income effects. It doesn't mean that that analysis would show progressivity or regressivity. It just means that this ex ante theorem about value of times doesn't mean anything for income effects. Okay, so then we extend now we've got everything set up. Home auto bus model. So it's exactly the same, we just throw a bus in there. So the principles of modeling the bus is the bus could really be anything that is like shared and runs in mixed traffic. So motor bus, streetcar, carpool, shared ride, dollar van, whatever. And then the important thing is that riding the bus is generally slower and cheaper, so it attracts low alpha trips. So we're going to see how does this change the calculus of who wins and who loses. So the analysis is just the same. So now we just use a subscript B for bus travel time and bus money cost. Just like we had a full cost of auto, now we have a full cost of bus for people with a given alpha, which is PB plus alpha TB. And then we also have this thing that we can just call the full cost of travel, which is the lower envelope of the two. Because people will choose, if somebody does travel, they're going to travel by whichever mode has the lower cost. So we say the B is the same for both modes. Bus is slower than auto, so that means TB is greater than TA. And then bus is cheaper than auto, so PB is less than TA. Which is the case for quite a few trips, especially if you count parking costs. So now we're going to do the same type of equilibrium. Okay, so now instead of having a single line that divides an H from an A, we actually have this lower envelope. This is a lower envelope of CB and CA. So CB has a lower intercept but a higher slope than CA does because the bus is cheaper but slower. So that means that for low alpha people, for people with an alpha below this number, which is alpha hat, they're going to choose bus if they do travel. And then for people with an alpha above alpha hat, they're going to choose auto if they travel, which makes sense. The people that take the bus, because it's cheaper but slower, will tend to have a lower value of time. So now, for a given toll, this is a given equilibrium, we have three groups, H, A, and B, bus travelers, auto travelers, people that don't travel, homers. And then the intercept of the lower envelope is just PB. These are just stating what I just said. Okay, so X is called the crux. And the point of that, the reason I name it is that when we increase a toll, we can tell a lot about the distribution of winners and losers by which direction. So obviously when we increase the toll, this full cost of travel line, C of alpha, it's going to change. Its slopes are going to change, maybe its intercept will change or something. So that means its crux, this point right here will change. And we can tell a lot about the distribution of winners and losers for a given toll increase by how the crux moves. So now we're going to talk about the toll increase for the auto bus model. They make two assumptions about this toll increase. One is mixed traffic. It just means that if the auto travel time falls, the bus travel time falls too, right? Or at least doesn't increase. And the other one is not like, that's kind of from just physics. This is not from physics, this is just from more like common sense. The bus agency isn't going to increase the fare at the same time they impose a toll. And this is just sort of, this simplifies the analysis. You could do it without this, but in real life, it's extremely realistic because in general, these tolls, the money is used to fund transit. So in the real life, whenever they do these tolls, they always dedicate the money to transit. So and also ridership on transit increases, so they get more fare revenue. Also, costs decrease because the buses run faster, right? So in real life, it doesn't happen. There's no reason to think it would. And by making this assumption, we greatly simplify the analysis, so we make it. Okay, so now what happens? This is just for a given toll. X can move into one of these three regions. In the paper, I go into like what each region means. The only thing that really matters, the only interesting case is a shift into region 3. So if X moves into 1 or 2, it could be shown that the new C, so C changes when we increase the toll. If X moves into 2 or 1, it can be shown that the new C is below the old C for everywhere. So everybody's better off. It's a Pareto improvement. It's not very realistic. Real life, you increase a toll, there's going to be some winners and losers, which is what we're interested in. But I'm just saying that theoretically it's possible, and that's what that's what an X into 2 or 1 means. But I'm not going to go into that because it's just kind of boring and I don't think it's relevant. So we're going to focus on shifts into region 3, which cause there to be some losers. All right, so this is what a shift into region 3 looks like. So this is the original full cost of travel. Now we have so that is C naught here because it's the before the toll increase. Now it moves to C1. So X has gone up there. So what we see is that we have basically wherever C naught exceeds C1, the full cost of travel has fallen for travelers with that alpha. And then wherever C1 exceeds C naught, the full cost of travel has risen for travelers with that alpha. And now we have a whole bunch of different categories, like population groups, like we did in the other one. Like this one is the people that did not take the bus before, but now that the bus goes faster and it's not any more expensive, they start to take the bus. HB plus, home bus, are better off. People that took the bus before, stayed on the bus, now it just goes faster, it's not more expensive, they're better off. Likewise, the people that have a very high value of time, they drive before and after, they are better off. And then, but then in the middle, and this is what's important, is that it's now the winners before everybody above a certain value, everybody with a sufficiently high value of time was better off, everybody with a sufficiently low value of time is better off. Now, people with low enough value of times are better off, right? Because they can just take the bus. People in BB plus, AB plus, HB plus. This AB plus is the people that drove before, but now that bus is like faster, they appreciate it, so now they start taking the bus and they're actually better off because they save money. The car is more expensive than the bus. Any case, but then in the middle you have these groups, AB minus, the people that switch to bus but don't like it. They wish that the toll had never been increased. You have the people that drove before and keep driving, but their value of travel time is not high enough to make them better off. And then the people that used to drive, and now that it's expensive and they don't value the travel time savings, they just quit driving. And then again, we still have the HH not group, which the people that just never travel, they're not affected. So I think one of the contributions of the paper basically is just being explicit about thinking about different types of people. Like so often when people talk about tolling, the entire focus is just on drivers. It ignores the bus riders. And also the entire focus is on just people that are tolled off the road. No one ever thinks about the fact that some people are tolled onto the road, people in HA plus. No one thinks, and people talk about drivers as a certain class, like they're all worse off or they're all better off. But really these are dedicated drivers, but some of them are better off and some of them are worse off. And then also, like if you get tolled off the road and you start riding the bus, you might actually be better off. So you can either be worse off or better off. It could go either way. So in a way, it's a little bit inconclusive, but the most important thing is just to note that now the value of travel time, it's not a either or thing. It's not everybody above a certain level is better off, everybody below a certain level is worse off. It's that the winners are on the ends. People with low values of time, people with high values of time, and the losers are in the middle, people with middle value of time. Again, this is even in the other case of the simple, we couldn't say anything about income regressivity. Now we definitely can't say anything about income. So don't think that it means that like middle class people are necessarily worse off. It might be, but you'd have to do an income analysis to establish that. Okay, so now we're going to get into a simulation. So all we did before was we had no model of how traffic works or no model of demands. We just sort of made assumptions like if the toll increases, traffic will get faster. Now we're going to make an actual model, a specific model in which that actually obtains. This model is a special case of what we call an MFD model or an NEF model. It's a description of a downtown with what's called a network exit function. So this is a more recent traffic flow theory discovery, which is that downtown traffic can kind of be collapsed. Instead of thinking about specific routes and such, you can just think about the downtown being kind of like on a particular road. The downtown has a relationship between the number of vehicles that are in the downtown at once, called the accumulation, and the aggregate flow in the downtown, or the average speed in the downtown. So this is a way of collapsing the state space of a downtown from thinking about the traffic on every single different link to just sort of a generic entity that is large. And so in this case, so it has a network exit function. Well, maybe we'll see what that, maybe it'll be a little bit clearer. I'll go a little bit fast through all this because I hate the parts of slides where they walk through equations. So you can just trust me on this or read the paper. But anyway, so speed depends on the space average density of autos. So to make it easier, we say there's no traffic from buses. That's not to say that buses don't cause traffic, but we'll say that the amount of buses on the road doesn't change substantially with our toll increase. And that is pretty realistic because typically these tolls cover a very small part of a large bus network. For example, the one in New York City is only in Lower Manhattan. The NYC bus network is massive. They're not going to change bus service like massively in Lower Manhattan in response to the toll. So the effect of buses is folded into just this constant, which is the free flow speed. And then every trip, we made that assumption that every trip was equivalent. So every trip has the same length L. In this font, it looks like a /, but it's an L. So we say that the trip length, the trip duration of an auto trip, given a certain density of autos, is just L over the speed of auto. And we have this functional form. It's just kind of a flexible one. So and then TAF is that'd be the free flow travel time of an auto trip. The bus auto travel time is the same of autos, but it has this penalty, which is accounted for by the sort of the wait time, the access and egress time. So then if you have the so GA is the exit rate, the rate at which auto trips begin and end in this downtown. It's a static model, so it just sort of the cars are perpetually coming in and leaving. So if this would be for a given KA, this is how many trips exit per time unit per lane distance unit. In any case, so now we go, that's like the supply side. Now we go to the demand side. We have to get distribution, so alpha and V. So we say the distribution of alpha is this thing called a Dagom distribution. I just chose this, it's hump shaped. A lot of social science variables like income and wealth and such are described by Dagoms pretty well. It has 3 parameters, so it's really flexible, so we can make it all different shapes. And then the distribution of V is actually conditional on alpha because we would like to have a correlation between someone's gross benefit and their value of time. So I've made it, it's a logit, it's logistically distributed, but with a mean that varies with the person's alpha. So so then if you want the joint distribution, you just multiply f of alpha times f of v given alpha of v given alpha. Anyway, so that's kind of trivial. There's all kinds of different demand distributions. You could do bivariate, log normal, whatever. Anyway, I'll go fast through this. This just gives you, for a given travel time of auto and prices of the different things, what the flow of autos is. This gives you the flow of bus trips. And then we plot these next to the supply curve, GS of A. And we plot it for 2 different levels of the toll. So this is the one that makes the most sense. Here we have flow on the x-axis, travel time of auto on the y-axis. And originally, this is the demand curve. So the blue is the supply curve. This is the demand curve. They meet at a certain point. And then when we increase the toll, the demand for autos shifts downwards. And now they meet at this point. So the flow of autos has declined. And also the equilibrium travel time has declined. But originally, it was like that. And then now it goes down to that. So when we increase the toll, number of people choosing auto declines, the travel time of auto declines. And thus, the travel time of bus declines too. This is the same thing, just represented in density flow space. This is flow time space, use density flow space. You can represent their equivalent to each other. But the important thing is just that this equilibrium changes. So the density of autos obviously also declines too. So again, this is not to say this is the model. This is a special case of a model satisfying the assumptions that we laid out earlier in the paper. So now we'll move on to the numerical thing. So now I've actually given you that contour plot that I promised you. This is the population distribution for that Dagum logistic joint distribution. And then this is a full cost of travel before and after. I chose all the parameters to give you that shift into X3. So just like the theory predicted, people in the middle are worse off, people below this point are better off because of the toll increase. So it has the same distribution the theory predicted. This is what's wonderful about doing this kind of thing. It's like when you derive everything and then you plug it into these equations and it comes out just like you expected. These are the aggregates, we won't really go into them. The most important aggregate probably is that the consumer surplus of all travelers together has actually risen because of the toll increase. So in a standard model of just like home auto, it will frequently be the case that the travelers are worse off and you have to count the government's revenues in order for total surplus to rise. All right, so that's the end of the bus paper. So I'm going to ask you to save all your applause at the end because it might go on too long. Okay, so typically demand curves strictly fall like this one. So actually a better example might be this one. So this is a demand curve, right? Flow demanded for a given travel time. So what we're going to see is the shocking revelation that with shared rides, actually travel curves can bend backwards, and then you can get multiple equilibrium. So what I mean by share rides, if you haven't seen it, Uber Pool and Lyft Line, these companies really want to encourage this carpooling options, right? And there's other companies that facilitate more traditional carpools where the driver isn't a professional, they're just going to work. And then also, one of the, in these visions of our AV future, which will come eventually, I don't know when, one of the ideas that people have talked about is that in downtowns, there'll just be all these AVs circulating all around, and then whenever you want to drive, pulls up, and there might even be a driver there, right? So you can put 5 people in a little car, and then you get where you're going, and because of the matching, the origin destination of everybody in the car is very similar. So this is sort of thinking of a world in which shared rides are a much bigger part of traffic and a much more viable option for more people. We'll see that the demand curve can bend backwards, and we can get multiple equilibrium. Okay, so how do we get that? So again, very similar, but now instead of people can choose now between alone. So whereas before we called it auto, now both modes are auto, but this one's called alone. And there's shared, which is going to be a subscript S, and then once again the same trimodal choice with a expensive, fast alone mode and a shared, slower, cheaper mode. And then money costs is that you have PA is the cost of a loan. The papers line up very well as far as terminology. And then you have the PS, which is less than the cost of, so PS is less than PA. And then now instead of, so I could have done something that had the same thing where people vary by their gross benefit and their value of time, but I decided to mix it up. Try to do something a little bit different. So you could do either way. So in this case, everybody has the same value. So everybody, so before, if you had a certain gross benefit, it was the same whether or not you took auto or bus. Now we're going to make it so that everybody has the same value of time, but your gross benefit is different between the two modes. You could do this analysis either way, but we just did this to be like more original. So this is your gross benefit if you take auto. This is your gross benefit if you take shared. So that just reflects the fact that people have tastes which vary. Like people just have like a given. Some people just don't really want to get in a shared ride with other people. Other people like me hate driving. So this kind of accounts for that. So the trip length, LA is the length of an alone trip. And here's the crucial thing. Shared rides are longer, physically longer, because you have to go out of your way to grab somebody else, right? And drop off somebody else. So this is what leads actually to the backward bending demand curve. There's actually 2 ways that you could think of a backward bending demand curve with shared rides. One of them has to do with the fact that just when more people take a shared ride service, they get matched better. You're able to find somebody that's closer to where you're going. That's not what we're going to, that's another part of the paper and the math of that. It's very complicated. So we're actually only going to talk about something that arises in a much simpler and comprehensible way that no one ever thought of before, which is the fact that shared rides are physically longer. So let T be the generic pace of traffic, minutes per distance unit. So it means the duration of an alone trip is LA, the length of an alone trip, times T. The duration of a shared trip is LS times T. Okay, so obviously TS is greater than TA because LS is greater than LA. So I'll kind of give it away. So the reason that the demand curve bends backwards is that suppose that a shared trip adds a ½ kilometer. So for right now, we're going to fix it. In the real paper, the extra ½ kilometer is allowed to vary, but we're going to fix it. So suppose that a shared trip takes an extra ½ kilometer. Now, you don't care about that distance. What you care about is the time penalty when you make your trip, right? So suppose the traffic's really bad, like a rush hour or something. The time penalty to taking a shared trip will be much larger at that time, right? So therefore, fewer people will take the shared trips. So therefore, lots of people will take alone trips, and traffic will then be bad. So it's kind of a self-fulfilling prophecy. It's an equilibrium, right? Again, shared trip traffic is bad. Shared trips take a long time. Few people choose shared trips, so therefore traffic is bad. Now you can think of another equilibrium, which is that traffic is light. So therefore, the time penalty, that extra ½ kilometer, doesn't take that long. So a lot of people are like, I'll save some money. I'll take the shared trip. So a lot of people do that. Traffic will be light, and then then people choose a shared trip. So those are examples of a low shared equilibrium and a high shared equilibrium, right? And obviously in between you could have middle shared or whatever, right? It depends on how things pan out. But that's the general intuition that we want to think about. So the big news is that cities don't just have like linear responses to things that they do. They can actually jump among equilibria that might be like really different from each other. You have two cities that are identical, and for no reason at all other than that self-fulfilling prophecy, one of them will have really high shared, one of them will have low shared in the future. So that's the general idea. Okay, so what does equilibrium look like here? I'll just talk about the plot. Okay, so basically, this is a full cost of shared, just like we had the full cost of auto in the other one, CS. This is a full cost of auto, so money cost plus LA times T times that alpha, which is the value of time. So if we plot CS and CA so we make, before we had like an alpha B space, now we have an epsilon S, epsilon A space, representing your taste for shared versus your taste for auto. So you plot the CS and CA. Obviously, if your alpha S is less than the full cost of shared, you're not going to take shared. And if your alpha A is less than the full cost of auto, you're not going to take auto. And in between we have like the dividing line, which is for people with a high, these are people, up here we have the people that they could take shared, but their taste for auto, their alpha A is much larger than their alpha S. So they choose auto, and likewise they have the shared group. So just like we had the ABH, or the ABH before, now we have an ASH, but it's like the same concept. Imagine a density plot with a contour plot with the population, and all the mass in here will be the flow of shared, mass in here will be the flow of auto, mass of here, people that might travel but they don't in this equilibrium. Exactly the same stuff. We integrate over the masses of the different parts of that plot. We come up with the flow of auto trips and the flow of shared trips. So this is crucial. A shared ride vehicle, this is why shared rides affect traffic differently. It has a higher occupancy than an alone vehicle. So let's suppose that let's suppose we had an autonomous vehicle system with no drivers. You could put 5 or 6 people in a car. In that case, phi might be 5. If you could have 6 people in a car, you would expect that the average occupancy of a shared ride would probably be around 5 or something, because some of the time, or after it drops off somebody before it picks up somebody else, it has an empty seat, right? Other times it might drop off 2 people in a row and only have 4, but it will never have more than 6. So if the maximum occupancy is like 6, you'd expect the average occupancy to be like 4 or 5, depending on how efficiently they can find new people. In any case, so the whole point is that when people switch from an alone trip to a shared trip, even though they're still on the road, they don't impact traffic as much. Whereas before, traveling a mile when you're alone, it means adding another vehicle kilometer to traffic. That'd be cool if you're having a mile and added 1 kilometer. But no, if you travel a kilometer in a car, you're adding 1 kilometer vehicle trip to traffic. If you travel a kilometer in a shared trip with an occupancy of 5, you're only adding 1/5 of a kilometer to traffic in a way. So the total flow demanded, Q is like flow, is the length of an auto trip times the flow of auto trips. And then likewise for shared trips, but it's divided by this 5 because the shared trips hold a bunch of people. G is like measured in like people, and Q is measured in like kilometers of travel. Whenever I go to, that's why I try to focus on the plots. It's really hard to remember all the notation, so don't worry about it. But so since the phi is greater than the ratio of these, a shared trip causes less flow. That's an assumption. Okay, so now we're going to talk about, just like before, how we had like the 2 full cost of travels that like pivoted, created all these new groups. Same thing, but in the new space. These are the people that do shared before and after the toll increase. These are the people that do auto before and after the toll increase. These are the people that, sorry, I'm not talking about toll increases. I'm talking about a decline in the travel time. This paper doesn't have tolls in it. It just talks about backward bending demand curves. So this is like if the travel time declines. This is the people that take shared before and after, auto before and after. People that start to take a loan once the travel time goes down. The people that start to take shared once the travel time goes down. And then this is the people that switch from a loan to shared when the travel time goes down. And the reason that we don't have anybody switching from shared to a loan when the travel time goes down is that because the length of a shared trip is longer than a loan trip, the difference in time between them declines, right? So like if it's like a minute per kilometer and one is a half kilometer longer and you go down by half a minute, then you save 30 seconds. The difference between the two, both modes travel times goes down, but the difference between them shrinks by 30 seconds. So that means some people switch from shared to a loan, but nobody switches from a loan to shared because the difference between them has declined. Does that make sense? So the whole function of the model is that shared trips are more affected by traffic because they're longer. So when traffic declines, shared trips benefit more. Some people switch from a loan to shared. Might not be that many people, but no one will switch from shared to a loan when traffic gets better. There'd be no reason to. You would have already been taking a loan in the first place. If the difference between the 2 options shrinks and then you switch to the other one, it's going to be because you're switching to the one that was worse in the first place. So anyway, so we do the same thing. We can integrate over these regions. And so essentially, we get the change in flow. So you go to the change, it's LA times the change in a loan flow, which is the additional people that start to take a loan. And then you also minus the people that switch from a loan to shared. And then you also have the additional traffic from additional shared trips. So basically, if so many people switch that this actually declines by a sufficient amount, then overall flow will go down too. And so here I program an example in which there is a backward bending demand curve. So the QS, just like it was before, is the supply curve, just from the MFD. And then the QD is the backward bending demand curve. And the thing is before, because the demand curve in the previous model, because the demand curve only went downward, it was only like that, they only, in the supply curve goes like that, they only intersected once. But in this model, because they're both going in the same direction, they can intersect all kinds of times. And for these parameters that I inputted, they intersect 3 times. Now, you need to do a stability analysis of whether or not these equilibria are stable and such. By my analysis, these 2 are stable, this one is not. But that's sort of beside the point. The overall point is just that what we've derived here from a pretty simple assumptions in a model, just basic traffic physics, basic thinking about the fact that, shared trips are a little bit longer, we've arrived at this fact, which is that you can have multiple equilibria in city traffic. So what does that mean for policy? It means that cities might want to think harder about the fact they can be completely different kinds of cities even without changing their populations or changing their people. They can wind up in totally different states. It also means that there could be what's called in dynamic analysis bifurcations or things like this, like new equilibria are created or old equilibria die. Suppose that you had a toll, for example. It might be that the demand curve starts to shift, and you see very small changes in traffic, and then a certain equilibria ceases to intersect the supply curve, and suddenly you leap to a totally different equilibria. So those are the kinds of kind of nonlinear and exotic behaviors that you would expect in the future of a world with a very high share of shared rides. Okay, and you don't even have to have AVs. It could just be that more and more people get comfortable with things like carpool and such. In the real paper, I don't know whether or not this is going to be in that paper, but maybe we're just going to tease it. But we also have a model in which, so what we've done here is that distance penalty to a shared ride was fixed. I was talking about half kilometer in my examples, but we say that no matter how many people take the shared ride, no matter what traffic is, it's always an extra half kilometer. In real life, you'd expect that as more and more people take shared rides, that extra half kilometer will actually shrink because they can find somebody with a really similar OD to you, origin destination pair to you, so they can grab somebody faster, or just along the way, they'll run into somebody that's just right off of your trip. So that actually leads to much more complicated dynamics because the equilibrium also involves the changing L, not just the changing travel time and flow. So I've left that out of this talk, but we have accounted for it, but it ultimately just leads to even more backward bendingness. In any case, so if y'all have any questions, my email address, or I think we have 10 minutes left that we can do questions here. All right, thank you very much. Yes.
I have two questions. First, sorry I missed the beginning. What's the purpose of this research? And do you want to build a model to be applied to real situations everywhere? I think basically those study what your data based is that.
Yeah, I won't do a data study anytime soon, but it would inform the discussions of how people talk about congestion pricing in downtowns. Right? Traditionally, they sort of neglect the role of bus drivers. So I'd like to have the bus riders, and drivers actually too. But I'd like the bus riders to figure more prominently in these discussions because they can account for a large share of the welfare changes, and this sort of makes it a much more explicit way to talk about the effects of different groups being affected. So the theoretical stuff, it doesn't always have to translate into empirics in exactly the same way. It can still, I think, just inform the kind of general discussions that we have in the public.
Yeah, because what I'm thinking is even you are the theoretical model,
Yeah.
you try to study.
Yeah.
But there's variables and in the data or you analyze.
Yeah. Yeah, you would study all
totally
this.
different let's say New York or Chicago.
Yeah, you'd have to, in order to do a real study, you have to do a analysis of your demand. Just like a marketing company, before they launch a new fish fillet at McDonald's or something, they go out and they test it. Before they do these tolls, they go out and they do surveys and stated preference and such that they can set the tolls correctly. So yeah, you have to, those demand functions, the F functions that I proposed, you'd actually have to estimate those in real life. And in real life, you would have many more dimensions. So I just had value of time and gross benefit. You would also want trip length, age, experience with transit, things like this. Yeah, you'd have to go a lot deeper. Okay. Yeah, go ahead.
Your value of time might be a function also what mode you choose to travel on. Right?
Yeah, you can have different, so that's another simplification, is that in real life, in real discrete choice models, you would assign a different alpha for each mode. So I boiled things down to 2 so that they can be represented on plots and such so that it can be easily analyzed. But the same kind of effects generally will still take place, it's just in more dimensions. Instead of lines intersecting, we have hyperplanes intersecting. Yeah.
Could you go back to the last slide of the first paper? The result of your analysis is C0 and C1 or the contour plot?
Well, these are the aggregates. The contour plot is just given. It's just a parameter of the simulation, so it doesn't change before or after. The mass above here is the people that choose each mode.
So this is a distribution of the people,
Mm-hmm.
and they're top.
It's just given, yeah. It's a given, yeah.
And why did you choose it like this?
Like I was saying, so that The distribution of value of time is a hump shape. So real studies give it a hump shape like this. There's not a lot of guidance. So then real logit models use logistic distributions for additive random utility terms like V. So then I just did that. I basically said value of time is distributed like the literature indicates. Additive randomness is distributed like and logistically like it indicates. But the most important thing is like the general shapes. So this shape is very flexible. You can have it different shapes, but it only has positive support because we made the assumption that people only have positive values of time. The logistic function, all it is unimodal. It has a really, like depending on what parameters you choose for it, it's going to have a bunch of different shapes, but it's just always going to be unimodal. So they're both extremely flexible. That's why I chose those ones. Yeah.
Thanks for the presentation. I was wondering, so as you know now people are putting autonomous and connected shuttles in the downtown area and the vehicles. So how will the methodology of your work and the conclusion will change if you have those autonomous and connected?
Yeah, so basically if you can add other modes to these models. But so for example, in this one, maybe you could have, instead of just 2 pieces of the line, you could add another mode and it would have its own costs and its own travel time. So then the line, as you add more modes, instead of being like this, the line will start to get like rounder, you know, because there'll be more, it's the lower envelope of a bunch of lines that emanate from over here on the axis. So it would start to get rounder. Yeah. So you could, and then you would have a bunch of different groups. You'd be like people that switch from bus to autonomous shuttle or something, or car to autonomous shuttle. That's what's, I think, another contribution is that you can expand the analysis to include more modes in a kind of a straightforward way. I mean, it becomes more complicated. So this is the first paper to do this. So I didn't want to make it like, you know, also have everything involved. In real life, you have street hail taxis and, you know, bicycles and all this stuff, right? Anyway, yeah, so that'd be in the first one. In the second one, you would have to, if you wanted to add a mode, you'd have to add, this would have to have like another dimension, like coming out, and you'd have to have the person's preference for that autonomous shuttle or something. And then you'd have to say, well, I mean, just intuitively, I would think a shuttle would be slower than an Uber pool and maybe cheaper because it has a bunch of people on it. So then, you know, this would be like a cube, and then you'd have like a plane separating the 3 modes. Yeah.
I have another question. So if I'm a car owner, I would probably always lean into driving my car, or I'm going to be more prone to it. But I was thinking, how would you incorporate this into your model?
So then you would have a high epsilon A, a very high. If you're, lots of people are car owners, but I have a car, but I take Uber Pool when I'm in the city. Like when I used to live in the Bay Area, I took Uber Pool all the time. But so that's not like a total determinant, but that would just, a person that was a dedicated car driver would just have a very high epsilon A.
Then if you consider car owners, your distribution, the plot contour, the blue cup plot contour would change, right?
No, that would just be part of what's given to you. You can make that contour be any contour you want. You can come up with a trimodal distribution if you want to. The contour is is like sort of the most flexible part. It's least fixed. You could have anything. What matters is the shapes of the lines.
But that contour is going to give you the shapes of the lines.
No, the line shapes don't depend on the contour. The contour is just what you take the shapes of the lines and then you integrate over those different regions, and then the contour just tells you how much mass winds up being in those regions. The line shapes come from the cost and the travel times of the different modes.
Okay.
Yeah, so like when we want to get the flows here, so this is so initially to find the auto users, you would integrate the contours in that A region, and to get the bus, you would integrate that. But the population could be anything, but you still do the same integral. All right.
Okay.
All right. Is that all the questions? I think we're out of time now.
Let's think.
All right. Well, everybody, thanks for coming out to listen to this. If anybody's interested, next semester I'm teaching a course in transportation economics. The ads are up. over on the down there. I don't have any ads up here, but it's from on Mondays and Wednesdays at 2 to 3. There's a 3 and 4 credit option. It's a lot of theory like this, but there's also case studies. But it's not statistical. It will not be econometrics. It's theory and case studies. And it's in CE. It's a 498 class. All right, thank you.
So before you guys leave, just a reminder that we have a writing workshop next week, so please come. Well, not after that. You'll get benefit from coming. Oh, yeah, no,